Awesome. Thanks very much.
Sorry.
Yeah, great. No worries. Thanks for the invitation. It's lovely to see you, even though remotely. So that's the plan for the talk is to describe to you the observational evidence for this significant event in the life of our galaxy, when we think it undergone a pretty important transformation from kind of its teenage years into the adult Milky Way as we know it. And the first question is, when did it happen? And of course, it happened a long time ago. And we could have guessed it without even using Gaia data. And that's because most of these transformations and most active periods in lives of galaxies were very long time ago, some 10 gigayears or so in the past at redshift around 2, the epoch in the universe known as the galactic, universal noon, right? So when the star formation peaked and when the merging was also happening at very high rate, right? So the left-hand side is the observational plot showing the star formation rate density as a function of redshift, and you can interpret some of it with the theoretical plot that is accompanying it on the right, and is the merger rate, right? So the number of mergers as a function of redshift, and you can see that the merger rate subsides drastically when you come closer from redshift 2 to redshift 0. So whatever happened in the Milky Way happened very long time ago, and that's kind of exciting and annoying at the same time. We have lots of theoretical predictions as to what have or as to what might have happened with the young Milky Way, and as a result of this active merging history. Of course, its disk, if it had a protodisk, would be destroyed or splashed, as we call it now, or puffed up. You can also change the orientation of the angular momentum of the baryons, so you can flip and swing the angular momentum or the disk of the galaxy. You can also induce bar formation and induce bar buckling also, and you can seed instabilities, and you can seed perturbations in the disk. You can see spiral arms. You can suppress star formation. You can also promote star formation. So a whole zoo of events could be unleashed or intimately connected to this active merging epoch. So what exactly happened with our galaxy, right? This particular galaxy, the Milky Way, of the menu that I just showed you, right? And how it went through this sequence of transformations will depend on the exact details of the accretion history and what the masses of those merging blocks were, how much gas they were bringing with themselves, and what the geometry and energetics of those interactions were, right? And that's the idea. Now we have this data from the amazing space observatory Gaia that we can hope to use to pin down some of these unknowns, right? The accretion history and the details of interactions. And it all works because in some space, namely the space of integrals of motion, these signatures of ancient accretion events preserve very well. And so here you have a beautiful animation from the Aquarius collaboration where each galactic blob is color-coded with one color. They all merge with the host and then are absorbed into the Milky Way. And what you can see is basically phase mix, and they phase mix, and the debris, the stellar debris, are redistributed throughout the virial volume of the Milky Way. And so it's very difficult to unpick this mess unless you translate into this space of integrals of motions, and here angular momentum and energy are shown. And you can see that if you color code debris from particular progenitor with a similar color scheme, you can see that they're preserved, they're frozen. Let's assume they are frozen in this space of integrals of motion. Well, that's the kind of the point of having integrals of motion. And the ideas that have been suggested and explored, more than 20 years ago now. And finally, a quarter of a century later, we can now test these ideas and see what we can learn. But so this was the theoretical foundation of how we can use this archaeological record to unpick the past of the Milky Way. But in parallel to that, we also had very brave and insightful forays into the kind of the observational side of the galactic archaeology. And I'm showing here essentially the same plane of observables, where on the x-axis I'm showing the eccentricity of stars somewhere in the vicinity of the sun, passing now through the vicinity of the sun. Of course, they don't live there all the time. And on the y-axis, the metallicity. And you can see how, from the classic paper by Agin, Lindenbell, and Sandage, this plane, our view of this plane evolved and kind of started to come into focus in the other classic paper by Chiba and Beers, 40 years later, and then another classic paper by Carollo, and that's already using, taking advantage of this amazing resource that is the Sloan Digital Sky Survey, kind of the survey that started it properly. The survey science was born with the data from the Sloan Digital Sky Survey. And you see the same plane, right? Metallicity from metal rich at the bottom of the y-axis to metal poor at the top of the y-axis, and how the metallicity and eccentricity are not completely decoupled. There are patterns, right? And these patterns were used in each of these three classic papers to say something different about, galaxy formation. So ELS saw evidence for monolithic collapse. Chiba and Beers saw evidence for mergers, and Carollo and collaborators saw, dual halo, whatever that means, right? It was still interesting, right? So we kind of stared at the same data and we interpreted it differently. Then there was also quite a significant prediction in the era before Gaia, right? And that prediction was, or a hypothesis if you want, right? And it was based on a very simple measurement of just the stellar halo density profile. So here's a cartoon of the radial profile of the stellar density, galactocentric radius, and the number counts of some tracer population. And what a number of people saw, including the author Alice Disson, in the halo of the Milky Way as a very prominent break, where kind of shallowish power law was replaced with a pretty steep power law at large distances. And this break in this power law behavior, of course, it's oversimplification to describe this a hodgepodge of the different accretion events with just a simple power law. But nonetheless, it's just treated as a feature extraction, right? So this was a very simple, crude feature extraction applied to the entire galactic stellar halo. But an important feature was found, right? That the break was detected with high prominence, right? And so what Alice Disson then said, that the prominence and the existence of this break can be linked directly to the accretion history of the Milky Way. And she interpreted it as the entire accretion history dominated by a relatively early massive accretion event, just reading it off using numerical simulation from the simple observational data. So now we are in a fortunate position to test these theories and to kind of say a few new words, looking at similar data, but actually much better data, right, with the Gaia satellite. So we started to play this game in Gaia DR1 when we had to do a few hacks to actually give us an interesting enough and large enough population of stellar halo tracers. And then the question was, how do we select halo stars from the sample of nearby stars, in the few kiloparsecs around the sun? And we kind of switched a little bit in our approach and decided not to select, not to apply any cuts. And partly the reason for that was already obvious in these planes that in these plots that I showed you, right? So there is no clear gap between the kind of subpopulations in the plane of metallicity and eccentricity. So you can't really draw a line that would neatly separate, the disk from the halo. And so motivated by that, we decided not to do that at all and model the entirety of the data with some flexible model. And the flexible model was provided by the extreme deconvolution approach, right? This is multi-Gaussian, kind of multivariate Gaussian fit-in that was described in a paper by Bobby, Hawk, and Russ. And it worked relatively well for the local velocity distribution, right? And so modeling the entirety of the local velocity distribution, we could have components kind of being responsible for the thick disk, for the different portions of the halo, and that worked well. And we could identify kind of dominant component in this decomposition that was clearly halo-like, and we could measure its properties, right? And so again, here we're doing very simple oversimplification kind of description of the complex velocity field with one parameter, right? And that one parameter is the orbital anisotropy, right? So it's basically telling you how the amplitude of motion in spherical polar coordinates in radial direction compares to the motion, the amplitude of motion in the tangential direction, right? So if beta is close to 1, that the largest amplitude of motion on the orbits of the sample of stars in the radial direction. And if beta is less than 0 and approaching large negative numbers, it's tangentially anisotropic. What we noticed immediately is this very strong dependence of the velocity anisotropy on metallicity, and that's what is shown in this plot, beta versus metallicity for the stars. It doesn't go very metal rich, so it's kind of, we were already biased in our view by our prior assumption or as to what the halo should look like, right? So we never kind of ventured in that in that analysis beyond the metallicity of -1, which is of course very silly. But you can see that even in the range we considered, the anisotropy evolves from not far from isotropic at low metallicities to very highly radially anisotropic at high metallicities. And you can imagine that not far from isotropy, so kind of roundish velocity ellipsoid, would be consistent with accretion of multiple small fragments from different directions onto the galaxy at different times and kind of mixing together to give you this isotropic distribution. And then the extreme radial anisotropy that we saw at the metal rich end of our sample implies a particular direction. It implies this kind of head-on interaction, radial direction of the interaction. But this is not the only observational evidence that we had in our hand that we could interpret, right? So there are 3 pieces of evidence, and I'm listing them all here, right? So the first of all, actually, it's the amount of stars, the number of stars that are sitting in this radially anisotropic component. And I'm showing you with number 1, the 2 views of the velocity distribution, the radial component on the x-axis and the tangential on the y-axis. And you can see that for the low metallicity, it is indeed roughly spherical, but for the higher metallicity, it's extremely radially stretched, right? So that's why we called it a sausage, right? It doesn't look like a Gaussian slightly flattened velocity ellipsoid. It's extremely elongated, stretched. But the important thing here to notice is the number of stars in each of these slices that are metallicity slices, right? They're shown in the top right corner. Most of the stars in the solar neighborhood, in the halo of the Milky Way in the solar neighborhood, are sitting in this one radially anisotropic component. And then the second piece of evidence is the metallicity, right? So we can estimate typical metallicity of the stars and then use metallicity stellar mass relation. So here's a version from Kirby 2013 using dwarf galaxies in and around the Milky Way. And you can see that dwarf galaxies are sitting on this mass metallicity relationship, which is basically, you can interpret it very simply, evidence for kind of feedback processes that happen in gravitational potentials of different depths, right? And so when you make the gravitational potential shallower and shallower, the processes that feedback processes have more or less the same energetics, irrespective of the the host environment. And so they are more efficient in kind of removing gas from a shallow potential, which then finds it more difficult to kind of hold on to the gas and reaccrete it to keep forming stars. As a result, galaxies that are low mass find it difficult to self-enrich themselves as fast as the higher mass galaxies. So that establishes this mass metallicity relationship, which we can use then to essentially read off from this correlation the mass of the progenitor galaxy, even though that galaxy is now, scattered all over the virial volume of the Milky Way, right? So we've measured the typical metallicity, and that gives us kind of typical, a rougher estimate of the stellar mass of the progenitor. So a few times 10 to the 8 in terms of stellar mass. And then the third important piece of evidence is then when we look at the numerical simulations, we can actually track the orbital anisotropies of the debris clouds that are left behind by particular accretion events, right? So we can just track back debris cloud to its progenitor and then ask ourselves a question: what was the mass of the progenitor? When was it accreted? And that's what's shown here. The accretion redshift is shown on the x-axis, and then the anisotropy of the debris cloud that particular progenitor left behind at redshift 0 in the solar vicinity is shown on the y-axis. And there are 3 different curves for 3 different progenitor masses. And you can see that only most massive progenitors, so the red curve, accreted roughly redshift 2, so 8 to 11 giga-years ago, can produce this highly anisotropic debris cloud in the solar vicinity. I mean, we can talk a bit more if you want later on about how it happens. And Eugene Vasilyev led a very nice paper discussing the process of kind of merging of a significantly, of a massive enough satellite galaxy onto a host, right, with the mass in the mass ratio regime between 1 to 2 to 1 to 15, which leads, due to a combination of several phenomena, leads to a strong radialization of the satellite orbits, and then it deposits in the last bout of disruption, it deposits its debris on highly radial orbits. So there's now also insight into what's the mechanics of this orbital radialization. So I invite you to look at Eugene's paper. So this was kind of investigation with Gaia-DR1, and it already opened a kind of a completely new, very sharp view into the very distant past of our galaxy. And then with the Gaia-DR2, there was a whole gallery of very beautiful plots and very beautiful lines of investigation, all pertaining to the same kind of epoch of formation of the stellar halo. And I'm just showing very briefly some of these pieces of analysis. And the very first was the color magnitude diagram showing on the left here. This is now absolute magnitude rather than apparent magnitude in the paper led by Karine Bogusiau. And you can see that if you select stars that have significant heliocentric tangential motion, which basically, if you translate into galactocentric coordinate frame, that means halo stars, right? Because significant heliocentric tangential motion means that the stars do not move together with our sun, so they don't have disk-like kinematics. So these highly tangential in heliocentric frame stars are halo stars, but what is striking about this plot, you can see a very clear split of the color magnitude sequences. You essentially see 2 sequences that are split horizontally, and in the simplest kind of model of this distribution, that horizontal or temperature split would correspond to a significant metallicity difference between the 2 halo populations. So essentially, you see 2 very different in terms of their metallicity halo population, and the question is what they are. And then several papers use Gaia-DR2 to point out what they could be. And so here's one paper by Misha Haywood and collaborators looking at the blue, and here now blue color corresponds to the color of the turnoff in the CMD, so bluer turnoff, so kind of hotter stars, and red is redder turnoff, so slightly cooler stars. So this is the color in the right hand plot. And this is the Turmeric diagram. So, right, you have the component Cartesian velocity component. V is now aligned with the motion of rotation of the sun, and the two other components essentially give you an idea of kind of the energy of the stars. And you can see that these two halo components are actually very different. There are stars that are overlapping completely in this velocity plane. They have very similar V and U plus W components, but you can see that typically the blue components, so the more metal poor, hotter turn off, have high energy, and they don't have many stars. This component, this sample doesn't have many stars that are co-rotating, while the red, kind of metal richer, hotter turn off stars, while having low energy on average, also has essentially can be viewed as a long tail stretching from the disk, and the disk is absent here, right? It's the wide gap around zero, V of zero, right? So they had to excise that region of the Turmeric diagram. So the two components, very different metallicity, very beautifully shown, and the interpretation, of course, has been in the air and in the literature, and it's kind of the accreted part of the halo and the part of the halo that was created in situ. If there was a massive event long time ago, surely it would have brought some subsystems with it. So immediately we looked for the globular clusters that could be associated with that progenitor galaxy. And there is a clump, if you look at the orbital properties of globular clusters. Again, Gaia now just completely revolutionized that field, right? So we have very precise information on the orbital properties of many globular clusters. And so we can make these plots that we never dreamt of making before. So this is upper center versus pericenter, and you can see that there is a clump of globular clusters with very similar orbital properties that we think were once part of that dwarf galaxy. You could also track individual stars, and what I've been telling you up to now is looking at stuff right in front of our faces, right? The solar neighborhood stellar halo studies. And in this paper that Alice Disson led, she compared the local stellar halo tracers, so, and they're shown on the left-hand side, with distant halo stellar halo tracers. And she split them by metallicity, so blue metal poor, red metal rich. And you can see that irrespective of where you look, nearby to the sun or far away from the sun, metal rich stellar halo is doing something very different from the metal poor stellar halo. It's again this dichotomy between a meatball and the sausage, between the roughly spherical velocity distribution and highly radially anisotropic velocity distribution. And then, of course, follow up using Gaia, but now going into a higher dimensional space and looking at a bit more interesting, more detailed chemistry of the stellar populations involved. And now tying together detailed chemistry. And so here I'm saying detailed, but actually just one more chemical dimension added, the abundance of light elements, alpha elements, is now compared to the metallicity, right? So all these plots from 3 different papers by Helmy et al., by Makarev et al., and by Timoteo et al., showing more or less the same thing, which is the alpha versus iron behavior of stars near to the sun. But now we properties. And you can see it, these plots are kind of analogous to each other, right? So the eccentricity of the orbit is used to highlight a particular population. You can see that the highly eccentric populations, these group in particular, these group in particular, and these group in particular, all are sitting on a very tight sequence, which can be interpreted as a sequence belonging to one progenitor galaxy, right? And you can see that it actually, managed to self-enrich to pretty high values, right? To minus 0.7 or so. So it's kind of now overlapping with thin and thick disk, right? So that's very interesting. But already in these plots, you already see that the highly eccentric halo stars also exist in a completely different regime that are even more metal rich and much higher alpha. And that's this in situ component that I highlighted before. So now I'm going to kind of jump and say, well, let's look at, let's try to interpret some of this data with more sophisticated simulation. So we've looked at the cosmological hydrodynamical simulations. In particular, this is the Auriga Suite, and this is the project, very successful project led by Rob Grant. So there are 30 Milky Way-like galaxies in this suite. And what we wanted to do is to treat them just like we would treat the Gaia data, right? So we applied the same idea of multivariate, multi-Gaussian decomposition. So it is applied to Gaia DR2, and we fit multiple components. And this is now the residual showing that it kind of works, especially for the halo. And then you can do this, but it's much easier to do it for the simulated galaxies. And the velocity fields are shown at the top. This is, again, I remind you, radial component of velocity versus tangential. And the top row, all stars in solar vicinity. The middle row is only accreted stars. And then the bottom row is the result of our multivariate, multi-component decomposition. These are residuals, right? And you can see that the behavior of the velocity ellipsoid of the accreted stars, right, once you've gotten rid of the in situ population, is different in different Auriga hosts. So Auriga host is given with number at the top, right? Some have a pronounced sausage-like, very stretched, right? They don't look like a flattened Gaussian anymore. Very stretched radially distribution, and some look a lot more spherically symmetric, and some look pretty much round, right? So there is a variety of outcomes of a formation of Milky Way galaxies. So all these galaxies were supposed to be like Milky Way, but not all of them are actually like Milky Way at all, right? And so our quest was can we identify those Auriga examples that have an equivalent of this Gaia sausage structure in velocity space around the sun. And it's pretty straightforward to do, and that's the result of this decomposition is shown here. On the left-hand side, we're showing the beta, the orbital anisotropy of the dominant component in the stellar halo next to the sun, and the x-axis is kind of a fractional contribution to the halo overall. And because we know what it is in the Milky Way, we know that 2/3, as I showed you earlier, belong to this high beta component in the actual real Milky Way. And the beta is of order between 0.8 to 0.95. We can select a particular corner of this plane. Again, this is feature extraction, very crude feature extraction, but nonetheless that allows us to pin down the likely analogs of our galaxy in this suite of simulation, right? So when we select galaxies in this corner, we can now plot their mass assembly history, which is shown on the right, and this is cumulative mass as a function of look back time now. So sorry, that's not look back time. The time here is time from Big Bang, right? So the redshift 0 is here. Okay, that's when it reaches 1. Okay, so that's important distinction. And the red curve is all the galaxies that sit in this corner, and the blue curve are all the other galaxies. And you can see that the galaxies in that top right corner had a rather different mass assembly history. They all kind of underwent this rapid buildup some 8 to 11 gigayears ago, right? While the other galaxies, there is a spread, of course, there is diversity. We're not saying, we can zoom in on a particular accretion history. There is diversity, but there is also bulk behavior that is different between these two samples. And that's very important. And of course, with simulations, you can do magic, like just tell me what was the mass of that progenitor and when was it accreted, right? And you can see the distributions, again, are broad, but there is a preference for rather massive in terms of stellar mass, right? The x-axis shows the stellar mass of the progenitor and relatively ancient event, right? So again, there is a spread, but there are events between 5 to 12 to 10 gigayears. Sorry, this is again merger time, right? So you have to subtract 14 gigayears, right? So this will be 7 to 11 gigayears ago. So all kind of checks out, and but now you have direct correspondence in this high-resolution cosmological hydrodynamical simulation that you can deduce a lot more about the properties of that event. So what was always kind of slightly unsatisfactory to me was that we've been building these pictures of the formation of the stellar halo and kind of transformation of the Milky Way based on a very small and very local sample of stars. These are all the stars that Gaia measures rather well. They are within few kiloparsecs of the sun, right? This is a minuscule fraction of the virial volume of the Milky Way. And of course, you know, when you assume continuity, right, kind of the typical assumption of galactic dynamics, right, you can reconstruct what happens in spatial dimensions as well if you understand your velocity field, right? But it would be also nice to look just at the spatial properties of this debris cloud, right? And so for this, you need a different set of tracers. And you can use our Lyra, which in Gaia are still pretty distant, right? So given the intrinsic luminosity of an Lyra using Gaia's limits in magnitude, you can see them out to 100 kiloparsecs from the sun. So that's good enough to sample kind of the inner, most of the inner halo of the Milky Way. And so that's the distribution of the density of the Lyra stars. And that's just projections on the principal planes in Cartesian galactocentric coordinate frame. And the grayscale is the data, the density, and the blue contours just show you the contours around that data. But the yellow contours, the dashed, the orange contours, is actually a model, right? And that's the model that was again built using a Hawk in DR1, selecting our Lyra from kind of variability that was picked out from the photometric error on each star in the Gaia DR1. So that worked actually pretty nicely because now this model from DR1 is validated here from the true Gaia consortium classified sample of our Lyra stars. And you can see that model describes the distribution of our Lyra throughout this volume that is roughly 100 kiloparsec on the side pretty well. And this distribution is triaxial. There is a principal axis that is not far off kind of the plane of the LMC and SMC infall, right? So it's this kind of direction perpendicular to the vector from the sun towards galactic center. So I'm showing where the sun is, right? So that's interesting that this principal axis is kind of sitting in that plane. And you can see that this triaxial structure is also kind of tilted out of the galactic disk plane, which is excised here for various reasons. But one of the reasons I'll mention briefly, and that was with this analysis and the subsequent analysis, we, to our great surprise, discovered that the galactic thin disk contains a pretty large number of our Lyra. And that's actually not predicted and is contradictory to the classical stellar evolution theory, but I'll come back to it in a sec. So how do we know that this particular structure, which I just showed you, right? This is the debris cloud left behind by the merger event that I was just talking about. And for this, you need to look at the kinematics. And of course, with the Lyra, you don't have all 6 components of the phase space information. You only have 5. Line of sight velocity is missing, but you can look at the projection of the velocity ellipsoid on the sky, right? And if the velocity ellipsoid is highly stretched, right, and then the galactic mu-L and mu-B components will be correlated highly, right? So that's what you will see. You will essentially see the projection of the ellipsoid. That's thing number one. And another thing to note is that if you have a head-on collision and a highly eccentric orbit, then around a particular location in the galaxy, say around the solar radius, if you look at the radial velocity, you will have this bimodal 2-hump structure. And that's because you slice in this chevron which is shown here in VR versus R, right? And most of the stars are basically on radial orbits. They're either coming in or coming out. And the only stars that will have low VRs, right, low radial velocity, will be stars that are turning around. And there are not many of them actually, right, given the geometry and energetics of the event. So mostly you'll see high negative radial velocity and high positive radial velocity. So we can, interpret these insights when we look at the data. So here's the data compared to very simple toy models. And these are just projection. These are actually, correlation coefficients between mu L and mu B, right? And they're shown projected on the sky, on the heliocentric galactic sky, right? So you can see that if you have an isotropic velocity ellipsoid, you see no correlation whatsoever. You have a, round velocity ellipsoid. If you have tangentially anisotropic behavior, you have a particular pattern of essentially anti-correlation between mu L and mu B. And if you have radially anisotropic behavior, you will see this pattern, which is positive correlation between mu L and mu B. And so the final panel on the right-hand bottom corner shows the data, and you can see that the data, which just shows the correlation between mu L and mu B, is very similar in terms of the pattern of the change of the correlation to this highly radially anisotropic model, which is shown in the bottom left. So what it's telling you is that this, and the stars that are shown here are all the stars within 20 or 30 kiloparsec from the center of the galaxy. So all the stars within 30 kpc from the galactic center are participating in the same kind of motion. They're going in and out on these highly stretched radial orbits. You can actually do something much more sophisticated, and you can try to fit this two-hump model to the 5D data, right? So you can assume a symmetry and then kind of reconstruct the behavior of the velocity ellipsoid and the separation of these two humps in the chevron pattern that I showed you here. So this 2LR distance is the distance between the two sides of chevron, right? Or here between two humps in VR space. And that's what we can do by modeling the kinematics of the Auriga Lyra throughout the halo of the Milky Way. The LR is shown as a function of distance. And you can basically see this chevron pattern where not far from the pericenter of the orbit, the VR separation reaches maximum and then drops where the orbits are turning around. And then it also decreases slowly out to the apocenter, to the last apocenter of the progenitor galaxy, and the kind of the synchronized apocenter of many of the stars that were unbound from that galaxy. And this is one-dimensional plot, and on the top right, I'm showing kind of two-dimensional plot. This is now in ZR, and I'm color coding by this kind of separation of the two humps in VR space. And you can see that the very central 4-5 kiloparsecs, you almost don't see these two humps at all, right? And that's because the pericenter of the orbit was probably close to there, so it had some angular momentum as it disrupted. So what it means is probably the very inner portions of the stellar halo are also not dominated by the debris from that particular galaxy. And so if you're interested in this unexpected discovery, I recommend you to look at the paper that is led by Juliana Iorio that looks at the chemokinematics of the Gaia Lyra and proves with a very careful analysis that there is indeed a large number of very metal-rich and very young Lyra with thin disk kinematics. And that's, if you read the literature, that's completely, I'm calling it unexpected, but it's actually not unexpected because glimpses of this have been seen in observations for last 30 years or so, but it hasn't been seen with such precision. We haven't mapped the kinematics of these stars across a large range of galactocentric radii to show that their velocity dispersion profile is very close to the velocity dispersion profile of a thin disk with ages between 2 to 5 gigayears, right? Because of the age dispersion correlation, you can actually now say what the ages of these stars are. And they have impossible ages, right? So the age of 3 gigayears is impossible for an RLI. It takes much longer for a single star to live on the main sequence before it evolves up and then descends onto the horizontal branch. So this is kind of a huge class of imposters, of RLI imposters, that was discovered as part of this analysis. So now I have some time left to talk to you about the response of the Milky Way. I, of course, already alluded to some of it, namely splashing of the galactic disk and formation of the in situ halo. But there are other things that are interesting, and there are things that are interesting about this splash component or the in situ component that we think was created as a result of that merger, right? And I'm going to ask Ted how generous is he? How much time do I have to talk about the response? Do I have 5-10 minutes?
Yeah, I think we can be generous. Yeah, go ahead.
Half an hour, 40 minutes.
5-10 minutes would be fine.
Yeah, I mean, you guys. I mean, I guess I'm
be speaking to you in 40 minutes time, but if you want to do that, that's fine. Yeah.
Yeah. So I have basically in this part of the talk, I'm focusing on something that has been published and has been discussed, and that's the splash component. And I would be maybe I leave it aside now because maybe there is more exposure to this particular response of the Milky Way. But I'll just summarize it very briefly. It's the in situ halo kind of component of the stellar halo, and it's been seen before in this paper that is a cult paper by Nissen and Schuster, who identified two distinct chemically components of the halo that had also slightly different orbital properties. And one is much more metal rich. Note that here color coding do not match. In Haywood et al. Paper and in Nissen and Schuster paper, the red and blue are switched around. But there is basically metal-rich high alpha halo, which is in situ halo, and it has to be in situ because it's just way too high alpha and way too high metallicity. So you cannot create this in a galaxy. And there were glimpses of these again in DR1, and that's pioneering work of Anna Banatsa that I have to admit that I didn't believe on the first sight, and I was very skeptical. But I think it's really cool that Anna actually deciphered these signatures with very few stars and highlighted the existence of this in situ population. And now the question is what we can learn from it, and that's dependent on how carefully and how much information we can extract about this in situ component. And so what I want to highlight to you is that while the accreted component of the halo has been studied intensely and been paid attention a lot. I worked a lot on it, and so I kind of know it and love it. But the in situ component has been kind of hidden. For me, it was hidden because it was just at a completely different metallicity, so I just didn't know how to look for it, right? But we know a lot less about it, but it nonetheless contains a lot of information about the prehistoric Milky Way. And so there are attempts now on the way, for example, to measure the age properties of this component and to measure the structural properties. And so one of the first attempts is by the group by Carmi Gallard, where they tried to estimate the age distribution. So the conclusion they came, and it's shown on the left, that the accreted and the in situ halos have completely identical star formation histories, very similar age distribution. And we tried to do this in this paper about the biggest splash, and we came to a very different conclusion, right? So we think that the two star formation histories, or the age distribution, whatever you call it, are synchronized in the sense that they have the same truncation age, right? So around 9 gigayears or so, they both were truncated. But if you look at the black histogram, that's in situ halo, and blue histogram, that's accreted halo, they look quite different, right? And so, and again, I think there are good reasons to believe that they should be different, because these are galaxies of very different masses trying to, self-pollute, self-enrich, and form stars as quickly as they can. So you don't expect them to be entirely different. But you can then use the fact, for example, the simple fact that they both age distributions are synchronized in terms of their truncation. So if you can measure the age distribution of the in situ halo, that tells you when this merger event took place. And here I'm kind of showing you the data, how I identified very crudely different components in the space that I thought was very, neat, and gave to me a new insight onto kind of how the galaxy was put together. And it's the space of azimuthal velocity phi on the y-axis and age, right? And you can do these things now because of Gaia, and for stars like turn-off stars, suddenly you have a pretty good uncertainty, pretty small uncertainty on the spectrophotometric ages. So now with DR3, in less than half a year, we'll have a ton of main sequence turn-off stars. So we'll be able to do it even better. I'm not going to go into detail of how to interpret it with simulations. What I'll show you here is in simulations, you can now take the in situ component that is basically proto-disk of the Milky Way splashed up by this massive major merger, and look at its spatial density, right? And this is ZX slice through the density, and the splash or the in situ halo shown is in red contours. And it's actually much smaller than the accreted halo that is very diffuse and stretches out all the way to the virial radius. It's like a puffed up bulge, right? Now you can finally trace it in the Milky Way in the same spatial plane, and that's shown on the right-hand side. And we're doing it here with our Lyra again, but these are particular Lyra. These are metal-rich Lyra, and you can see that they're sitting only in the very inner part of the Milky Way, and they're tracing this in situ component, and it's quite small. It's it's out to 10 kpc in R, in maybe 5 to 7 kpc in Z. So it's flattened, like in the simulations. Expectedly, it came up from the disk, but it's very small. And so what I think is interesting here is that you can use this to put constraints on what exactly happened with the Milky Way, right? Because it's telling you, how impactful that interaction was. But also it will, on the other hand, will allow you to benchmark your simulations of galaxy formation, because we still are using subgrid recipes to control our star formation, right? And so the extent and the amount of stellar mass and the in situ halo is telling us a lot about, this knob that controls the star formation efficiency at those ages. And the last thing, like literally in 2-3 minutes, is the new thing to me, because I guess I'm ignorant, but I think it's an exciting thing, and then maybe that can promote some discussion, or maybe you already understand it completely and you'll just tell me the answer. And that came out as part of this investigation that was led by Adam Dillamore, who is the first author on this paper. It's his master's project, and he kind of tried to look at comprehensive picture of all sorts of transformations that could happen to Milky Way-like galaxy as a result of a massive merger in the young, in the ancient history, in the young the age of the galaxy. And one thing that Adam found was this swinging or flipping of the disk of the Milky Way. So these simulations, we analyzed the same way we treated Auriga. We looked for the sausage component in the local stellar halo, and we then looked at these only at those hosts that had this sausage, and kind of believing that they're more like the Milky Way, the real Milky Way. And so what you see here is the angle between the present day and the direction of the angular momentum of the disk. I'm talking about the top row, and the direction of the angular momentum of the disk of the Milky Way at some time, look back time is shown on the x-axis, right? And you can do it for all stars, that's blue curve, dash, and then and the dashed orange curve is only old in situ stars. So the stars were born before the merger, and they're doing the same thing. And the merger time is shown by this vertical dashed line. And what you can see in all cases is that the direction of the angular momentum of the Milky Way's disk is swinging by quite a lot. And in some cases, it's flipping by kind of 90 degrees, like in the central column shown here in G23 on a very short time scale, right? So in 1 or 2 gigayears, the Milky Way's disk completely changes direction. And it's completely synchronized with that massive merger event, right? However, I think it's very difficult to attribute this swinging, and maybe I'm wrong here. Again, it's more intuition kind of backed up somewhat by the data from the simulation. It's very difficult to attribute all of the swinging to the progenitor dwarf galaxy alone, right? And the reason for that is shown here, and that's the total mass in dark matter as a function of look back time in the top row. In the inner 30 kiloparsecs, that's the blue curve, and in the outer 30 to 100 kiloparsecs, that's the orange curve. And you can see that the inner Milky Way, the dark matter halo, hasn't actually received much mass around the time of that massive merger accretion. So actually not a lot of mass entered the region where the disk is sitting, right? However, a lot of mass was dumped on the outskirts of the halo, and that's what's shown in the orange curve that goes up by quite a lot. And you can actually see that it goes up by a lot more than that dwarf progenitor galaxy was bringing by itself. So what we see is that dwarf galaxy was just one big lump in a kind of an epoch of prolific accretion, and during which a lot of mass was dumped on the Milky Way. And the Milky Way then changed its shape, and then the shape evolution is shown in the bottom row, right? So it's kind of changing shape from highly triaxial to becoming much more spherical as a result of this accretion. And so this all comes together if you look at the red dotted and green dash dotted curves, which show you the minor axis of the dark matter halo. And you can see that that direction is also changing with time and also flipping similarly to the galactic disk. But when you look at G23, you can see that essentially the outer shells of the dark matter halo in this particular case rearrange themselves first, and then that kind of triggers the torques the inner parts of the galaxy, and then rearranges the inner dark matter halo, and then finally later on the disk. So that's kind of the current my current understanding, that it's that dwarf galaxy that we see and use as it's basically just a marker of a particular accretion event, but a lot more mass was dumped on the Milky Way, and it could potentially unleash this kind of dragging and swinging and flipping of the angular momentum axis. So I finish here. These are just the conclusions. I thank you very much for surviving this talk that lasted now a very long time. I'll just go through this quickly, say that the disk was heated, splashed, probably flipped, it transitioned from thick to thin later on, maybe bar formed, please look in Adam Dillamore's paper. And then there are some open questions that I think are related to all this, and I'll stop here. Thank you very much.
Vasily, we'll give you a virtual round of applause.
Thank you.
Great, thank you very much. Is there any questions for Vasily in the room? That's okay. Okay, so Julio has a question, so I'll let him go first. Go ahead, Julio.
Well, thanks. Thanks, Ted, and thanks, Vasily, for a wonderful talk. I mean, amazing work, of course. I guess since you mentioned history a few times here, let me show my age and add a historical note to the Gaia Enceladus sausage, discovery. This is actually very easily seen also in the Hipparchus data sets. I mean, when I started looking at this in the early 2000s, we actually found that there was a very significant peak of low angular momentum stars in the metal poor halo that were slightly counter-rotating, that were had lower alpha enhancements than the typical halo, and that they had associated globular clusters. And so all these things were actually written up. And I think it is exactly the same structure that was written up in Mesa, Italia in 2005. And we wrote a sequel on that in 2011.
Yeah.
And, sorry, just to add a historical note to it. But of course, what we missed at the time was, because, the samples were so incomplete and so small, only 150 stars, is the importance of this event in actually setting up most of the properties of the halo, which of course is what you and other people have done with Gaia, and which is of course quite amazing. So it was just a comment on that.
Thank you, Julio. Yes, yes, I agree that indeed Mesa et al. Paper kind of showed glimpses of this particular, of an accretion event, and then. Yeah, I guess you're right that the interpretation as to how important it is for the, is it just a fragment, or is it like what we're trying to say, the bulk of the stellar halo? That was, you needed Gaia and a kind of a bigger view of the halo to conclude that. Yeah, and you're right.
Great. Scott, I want to ask you a question.
Sure. You've argued that the orientation of the disk is changing. That is, the disk is sort of precessing in response to these accretion events. Mm-hmm. If it's precessing at the current day, if the twist is continuing up to the current epoch, can you see that twist in the Gaia astrometry of the disk stars relative to the quasars?
That's exactly the question, Scott, we are asking ourselves. So the interesting thing is that if you just plot the kind of this precession or whatever drag rate across most of the Milky Way halos in our sample of like Milky Way-like subsample from Artemis, the mean precession is not small. It's like 10 to 15 degrees per gigayear. It's pretty high, and I think it should be detectable. Of course, this will be. Right, this kind of this tilt, tipping of the disk, right? This will be kind of, we need to be careful, right? You want to see kind of large scale kind of dipole, right? So one side of the disk is moving one way, the other side moving another way. So I think, yes, that should be doable. And I would like to test that indeed, yeah.
So is there like a relationship between that and the warp that is seen in the stars in the Milky Way, or is that a different thing?
I think I don't know. I think the warp is probably much more recent and unconnected, but it will complicate the analysis, obviously.
Right, yeah. Okay. Peter, do you want to?
Hi, thanks for your great talk.
Hey.
You told us about the Gaia sausage and that it was long ago, and it was part of a big train wreck, so what was happening, maybe more of them. But then you also said that in one projection, it kind of looked like it was related to the LMC. So would that be a coincidence, or is the LMC part of that train wreck that got captured and didn't merge, or what's going on?
Okay, so that's a really good question, and thanks for kind of noticing that. And I think, to me, this is a very interesting question that could potentially lead to clarifying some of the mysterious properties of the Milky Way. But I think it's a little bit tricky to pin down. So so that direction is measured very well with the, say, RLI, this triaxial structure and its major axis. I think we're quite confident about that. So now, when you look in the N-body simulations, when the merger concludes and then the phase mixing of its debris continues, right, that structure that forms, that cloud of stellar debris, sometimes there is figure rotation, sometimes there is no figure rotation. Sometimes basically phase mixing proceeds in a way that the orientation of the principal axis is preserved from 10 gigayears to redshift 0. And that direction stays more or less frozen. And in other simulations, it doesn't, right? It basically, there is some kind of figure rotation, and that triaxial cloud shows some rotation, and it moves away. And so you don't know what the original kind of direction of infall was, right? And so that's the problem, right? And so if it hasn't rotated away from its original orientation, then yes, there is something to it, and we can try to interpret it, and maybe indeed there is connection to the kind of so I guess the next frontier in this analysis is to try to understand how the Milky Way connects to the large scale structure, or how it connects it to the large scale structure at redshifts 2 to 5, and so whether this particular event is a kind of a marker, a harbinger of a switch in the accretion direction, in switch in terms of which filaments will feed in the Milky Way. And that's why you see this such a drastic change in the orientation of the dark matter halo, right? And maybe it could be that then the accretion, the subsequent accretion, proceeded from that particular orientation. And so that's why we have, plane of satellites, and that's why we have LMC and SMC not far off from that plane. It could be all connected, but I'm not yet in a position to claim all that, but it could be possible, yeah. And so I think we have now have been collecting clues to try to help us. But I think the obvious next step to do is when we run cosmological zoom-in simulations, and we try to compare observed properties to the kind of this model mock Milky Ways. I think what needs to be done is we need to condition on the particular accretion history that we have uncovered with Gaia, right? So I think it's now time not to look at everything and kind of average over everything, but we know what happened in the Milky Way, so we should look, we should do our inference in a conditional sense, and so hopefully there'll be an answer soon.
Yeah, a quick follow-up on the connection to the web. So we have a companion, M31, or it has us. And would it have got hit at the same time by all of this mess of sausages coming in?
Well, are you asking whether it would have a kind of its accretion history peaking around the same time?
Yeah, exactly.
I think from the studies I know, I think the Milky Ways and M31's accretion histories are quite distinct, and so in terms of, right, so in that sense, maybe the very distant past of the M31 hasn't been explored for one reason, that there have been events later on, right, so 4, 5, 6 gigayears ago, that are pretty massive and kind of obscure, more distant events. So it's difficult to say. While in the Milky Way, the mass assembly happened rapidly 8, 10 years ago, and it kind of stayed quiescent. So we have this kind of privileged view of the distant past. And so it's difficult to say what happened exactly in M31 8, 10 years ago, but in detail, the accretion histories are very different, right?
Yeah.
So
okay, well, that answers my question in another way. We didn't get hit by these massive ones more recently, but M31 did. So that's an interesting thing to understand for two things in the same potential.
Yeah.
Thank you.
Okay, we've gone a little bit over time, so I think we should probably call it close to the formal seminar. So everybody thank Vasily again, and thank you very much for coming. I'll stop the recording.
Thanks for listening.